Hello everybody, good morning. So can you hear me? So please let me know if you can hear my voice and also you can see my broadcasting. Because recently I updated my computer system. Probably there would be some errors in the broadcasting. Please let me know if anything is working well so that I can start my lecture. Is it okay for you? So, okay. It seems that you are taking my lecture, the broadcasting, right? Okay, today let's talk about the energy and torsion. So please recall the diagram that I'm using, any times. For example, say I emphasize that. So we have we have force equilibrium. We have force equilibrium forces, and then we have here the stress and then strain and then displacement, isn't it? So force vector, displacement. So if you looked at my short communications, so now you understand that we need to use two base vectors to represent the stress state and the strain too. And here in analysis procedure, note that this is the flow of the information here. And then, but to use, there exists an energy pair. For example, here in structural member scale, what the external force is, this is the energy pair. The work is, work is what? Force. The energy pair for work is force and displacement. This is the energy pair, and then we call it the energy conjugate. And then another work pair in the material point level is stress and strain. That's why we always consider proper set of energy pair. If you consider the external force, the proper energy conjugate is the external displacement. Displacement measured at the nodal points. And then if you want to consider the material point level, then you need to consider stress and strain as the energy pair. Now, how about the member level? So if you want to consider internal forces, then in the case of actual members, then we need to consider the internal force, and then its energy pair is elongation, isn't it? So that's why we have the work conjugate here. So this is work conjugate. So to define deformation energy, so we need to consider the actual force as a function of the elongation, and then we need to integrate the term, the work done by the internal force over the elongation. So we have to integrate this, okay? In the case of linear elasticity, the actual internal actual force is linear function of the elongation. That's why we can draw a straight line as given in here. So we already discussed this relation before when we discussed the actual members. And then if you integrate this, because this is nothing but a triangular shape, then it becomes a half of stiffness times and then square of the elongation, okay? And then please make sure that because this is a linear elasticity, that's why we have, if you check the actual force and the elongation, in the case of linear elasticity, this is a straight line. So if you calculate the deformation energy is defined by the area under this curve enclosed by the curve and then the horizontal axis. This is the deformation energy. But only in the linear elasticity, this deformation energy is the same as complementary energy, which is the upper part of this relation. So please make sure that the control variable to define deformation energy is elongation, okay? Not the actual force. Please make sure that this is really important, okay? And for the complementary energy, the control variable is the actual force, okay? This is a very different thing. So only in linear elasticity, Let me check that. Ah, this is too small. Ah, Uchari, okay. Okay, I just found the problem. Maybe I have to change. I have to use another one. No, hold on a second. Hold on a second, please. Okay. Let's go back to this. Okay, now is it better now, right? So you can see this. Okay, so let me repeat what I explained you just before. All right, so here in our discussion, so I emphasize you several times that so we have so-called energy pair, isn't it right? This is our flow of analysis. So external force, and then we have stress state, and the strain, and the displacement, isn't it right? So if you consider the external forces, the energy pair to external forces is the displacement. So we have to consider so these two, the two components to calculate the external energy. If you go into the material point level, then we need to consider stress and strain to calculate the deformation energy density. Okay. And then a member level, so we need to use the internal force and the elongation. So please look at my lecture note. So if you look at my lecture note here, so look at this. So to calculate deformation energy, we need to integrate the internal force and over the elongation, okay? So only in the linear elasticity, the area under this load displacement relation is straight line. The area under this curve is equal to area upper this curve. They are same. The quantity is the same. U is equal to U star. The only in linear elasticity. Let me check if everything's right. Yeah, linear elasticity. Okay. Otherwise, it's not working. So, for instance, let's consider nonlinear behavior. For example, let's use a thicker one. Let's use nonlinear behavior and elongation. In the case of nonlinear materials, so it would behave like this, isn't it right? So if you calculate the deformation energy, so as I told you, the area under this curve is equal to the deformation energy, U, which is given by function of elongation. And that you can calculate the complementary energy, which is defined as the upper part of the load displacement relation. So in this case, even our naked eye, the complementary energies function of the actual force, they are not equal to each other, okay? They are not the same, okay? They are not, sorry, not this one. The numeric value, they are not the same, okay? This is a general case. So the case, deformation energy, the numeric value of deformation energy is equal to that of complementary energies only for the linear elasticity. Okay, so please keep in mind this point. Okay, similar to the one-dimensional problem, so we can first thing that we have to do is we need to find out the energy pair. The energy pair for torsional problem is internal torsional moment. By the way, sorry, this is error. It should be torsional moment, and then the angle of twist, isn't it right? So we have to integrate the torsional moment over the change of angle of twist. And then because this is the linear elasticity, there is a linear relation that the slope of this linear curve is given by the shear modulus and the polar momentum inertia divided by the length of the member. Okay, the square term. So let's plot the change of deformation energy. For example, if you plot, the deformation energy is a function of the displacement measure, the deformation measure, deformation energy. Then if you plot this, because this is square, so you can easily recognize that this is what? So quadratic, is it right? Quadratic. And then if you look at the curvature of this part, the curvature is what? Curvature is positive, isn't it? So we call this behavior is positive definite. Okay. So in advanced studies, you may encounter the term of quadratic, the energy or positive definitive behavior. Just I gave you an introduction for the energy argument. Okay, now let's talk about transmission of power by a circular shaft. If you look at the motor, motor and engine, okay, then we deliver the power to the machine device using the torsional moment. Okay, so as we mentioned, the first, let's define the external work. The work pair, the torsional moment. The work pair of torsional moment is what the angle of twist, isn't it right? That's why, for if the torsional moment is independent of the amount of the angle of twist, then we can calculate the work by the multiplication of torsional moment and the angle of twist. And then here power means the rate of the work, rate of time derivative of work, easily speaking. That's why the power P is denoted by the time derivative of work. So work, power is the time derivative of work. This is the definition, okay? This is the definition. So if you consider this problem, then because now the torsional moment, let's say the torsional moment is constant, and then let's say we have a change in the angle of twist, and then we can take a derivative of angle of twist with respect to time, and it becomes what? The angular velocity, is like 각속도, angular velocity. So omega here is angular velocity. In 우리말 we call it 각속도. Okay, 각속도. And then this angular velocity can be given in terms of frequency, isn't it right? The frequency is 1 over or the inverse of the period. Okay, so using the frequency. And then the frequency also represented by revolution per minute, so-called RPM. Okay, so frequency is equal to revolution per minute, RPM, divided by 60 seconds. And then now let's check on an interesting measure of the power. We typically use horsepower, 1마력, 2마력, 3마력. Actually, this horsepower, the unit of horsepower was developed in industrial revolution, 산업혁명 때 개발이 된 겁니다. So here to make sure that the unit of work is force times the length, the work done by force over distance. This is the unit of work. That's why the Newton times the length unit, this is given by joule, isn't it, joule? And then the unit of power, as I mentioned, this is time derivative of work, okay? So here you put the time derivative here. That's why the unit becomes what? The force and then the unit of velocity, okay? So the unit of power is typically we use watt. That's W, but it's rather confusing, but now this is the standard, we use watt. So here the relation between the 1 watt and the 1 horsepower is given here. The 1 horsepower is defined as the power done by 550 pounds over the speed of 1 feet per second. This is the definition of 1 horsepower. So 1 HP is, if you calculate this using considering the unit conversion, so we can find 1 horsepower is equal to 745.7 watt. Okay, this is definition of watt. And in our daily life, instead of watt, we use kilowatt and the megawatt. Yeah, the kilowatt means 1,000 times of watt. The reason that we use kilowatt or megawatt is the same as the reason that we use megapascal and kilopascal instead of pascal, because the unit of watt is too small to measure the energy or power that we use in our daily life. Okay? Any questions? All right, so this is the part for the energy in torsional problems. So let me take a 10 minutes break and we'll go to the next subject. Next subject is a non-circular section. So let's take 10 minutes break here.